Hello everyone. Today we will talk about the exploitation of a modern smartphone baseband. So this is our agenda for today. At the beginning we will do some introduction and show some related work, and then do some background for some necessary knowledge to understand this talk. And then we will show to you a bug of the baseband which we use in mobile point-to-own on a Huawei device. And then we will show to you how to deliver and exploit the bug. We will do a demo, and finally we will explore a little bit the concept of escaping from the baseband. And then we will do conclusions. So we are from Tencent Keen Security Lab, and previously we were known as Keen Team. And I'm Marco, and my main focus is hypervisor and baseband and firmware. And those are my colleagues.
I'm Muting and work as and is a member of the A03 team. Yeah.
And hello, I'm Tianyi. I'm also a CTF player, and I'm currently the captain of CTF team A0E and Triple E.
Okay, so about our security lab, we are a white hat security researcher, and we are based in Shanghai, in China. And you can see our blog and Twitter if you want to follow our research. Our research area are PC security, mobile security, baseband and firmware, virtualization, car security, and application security. So let's start talking about baseband. So there is a small amount of public research on baseband. This is most likely because the complexity of the baseband is quite high, and you have to deal with complex specification. So you need to study a lot of material in order to get to know this radio network. So the entry barrier is a little bit high. But nevertheless, we have billions of smartphones around the world, and most of them, they have a baseband processor, and this attack surface is reachable remotely, so it's important to study and audit. Usually a baseband can provide a first remote code execution bug that you can trigger over the air and start to compromise a smartphone without user interaction. So our talk will focus on the Huawei baseband because it was our work at the Mobile Point-to-Own 2017 where we successfully exploited it over there. But there are other works on other baseband. For example, there is work on Samsung Shannon, the Intel baseband, the Qualcomm baseband, and the MTK baseband. So how does a modern smartphone looks like? Maybe 20 years ago, or I don't know, 10 years ago, a phone was just a single CPU executing everything. And but now it's different. You have a main CPU, which is called the application processor, which is executing your main operating system, which can be, for example, Android or iOS. And then you have several other processors involved in other operations. And in the radio area, you have the baseband processor and the Wi-Fi and Bluetooth system on chip mainly. And the baseband handles the communication, the radio communication with many different types of network, such as 2G, 3G, 4G. So, for example, they could be GSM, UMTS, and LTE. And this kind of radio component can be attacked remotely over the air. So we just told you that you have an application processor and then you have a baseband, and they are two separate CPU, but they communicate each other, and usually they do it with a bus, which depending on the implementation could be USB, PCI Express, or shared memory. So since they are separate systems from each other, if you get remote code execution on the baseband, you run code inside the baseband. You don't run code on the application processor because those two are two separate CPU. But the advantage is that baseband lag behind in terms of mitigation compared to the application processor. For example, in the Huawei baseband, we noticed that they lack of ASLR and stack cookies, so the remote exploitation is easier. But this kind of lack of mitigation is not only on this baseband, it's widespread between basically all manufacturers. So why do we want to target the baseband? There are several reasons which can be an advantage. First, it's a less understood attack surface and less audited. Second one, it can be exploited remotely over the air, and potentially you can do it from very long distance. Because if you think about it, maybe your phone right now is connected to a base station several kilometers from here. The third reason is, like I said, the lack of mitigation. And often when a device, such as, for example, the iPhone has a Qualcomm baseband, maybe Apple doesn't have access to the source code of the baseband, so they cannot audit it themselves. So it's less people looking for bug there. And the last but not least reason, it's because of complexity, of course. So we need to interact with radio, so we need to know about radio technology. Luckily today, it's easier to do this kind of research thanks to software-defined radio. They are inexpensive electronic device, which allows you to run fake base station, basically. And with this fake base station, you can attack the baseband. And an example of this kind of product can be Blade RF or USRP. And there is a lot of open source software, but the only problem is that they cover only some radio stacks. And we will see why this will be a problem for us. So the traditional way to attack a baseband is to run a base station with a SDR. And the problem, why this is effective, is it because the old network like GSM, they don't have mutual authentication. So if I just go around with a SDR and my signal is stronger than the base station of the carrier, then your phone will connect to my SDR-based fake base station, and I can exploit your baseband. And like I said, we cannot use this approach in our case, unfortunately. So probably in the US, you already know what CDMA is, because it was popular in the US. And our bug will be in the CDMA part. So we needed to at least know what CDMA is. CDMA is a family of 3G network, which allow you to carry voice data and signaling data. So it was competing in some area of the world with UMTS. So to sum up, basically a baseband is a black box inside of your phone which runs a unspecified firmware, and it's kind of similar to an IoT device because they run like a real-time operating system, and they have tasks and they schedule those tasks, and each task is responsible for some layer or some component of the baseband. And the complexity is huge because if you take, for example, the GPRS or GSM specification, they are thousands of pages. So let's talk a little bit more about real-time operating system on baseband. Like I said, they run tasks, but what you need to know is that often there is a task for every network layer you can find in the protocol. So for example, if you take the mobility management layer, which is a GSM part, you are often able to find a task called MM, which is responsible for this part. So once you identify the correct task, you can check the message handler, because this kind of task, they communicate via IPC. And once you found this message handler, you can identify the function responsible for parsing and processing radio message, which is the one that the attacker controls. And you can start from here to audit for memory corruption bugs. So how do you start to find bugs? We need first, of course, to collect information, and we have three main area to get information. The first one is, of course, firmware. The second one is runtime information for some debugging, at least. And the third one is online information. So we will check those three. So the firmware for Huawei, we grabbed it from the file system of the smartphone. You can find a file called secbalong-modem.bin, and it's on the file system of the phone because the Android kernel will load it, and then it will pass it to the trusted execution environment to check the signature, and then load it into the baseband memory and start the baseband. Since we got this file, after some adjustment, we can just load it in IDA Pro and start the reverse engineering. As you know, if you do reverse engineering, if you have any kind of debugging or runtime information, it's very useful. On the Huawei baseband, there was some runtime shell called the C shell, but sadly now it has been removed on newer versions, so we cannot use it anymore. However, we found out that when you crash the baseband with some bug, it will output some log to the application processor and store it on the file system. And also, if you have kernel code execution, you can just read the baseband memory from physical memory of the device, starting from this address. And this kind of memory dump capability helped us a lot to adjust our exploit. We did some research online, and I mean, of course, you need to know the 3GPP specification. Since you are attacking radio network, you need to know how those networks work. And the second one, we found some leaked version of the source code. It was old, but it was very useful for reverse engineering. And then there is this small project, which also was quite useful because it documents the format of the non-volatile RAM for this baseband. So let's now go into the case study of the baseband. So this section of the presentation, we will first show the bug, then we will explain how we trigger it, and then how we exploited it. So our point-to-own vulnerability was in the CDMA part of the baseband, specifically in a part called the CDMA 1X SMS transport layer message, in a function that is responsible for some message called PRL. So at the bottom you can see like a very simplified version of the bug. But first, before we check the bug, we need to check what memcopy-s is. Memcopy-s is a more secure version of the memory copy. Instead of taking 3 parameters, which should be destination, source, and size, they take 4, because it's destination, destination size, source, and source size. In this way, they can check if the copy goes out of bound write or out of bound read in terms of length. So they can do this kind of check. And for example, if you are overflowing the destination, they will panic the baseband, and they will you cannot exploit this bug. And this kind of method is a little bit maybe primitive, but it kills a lot of bugs actually purely by chance. And luckily, our bug is not affected by this because we control the offset of the destination. So let's check again the bug. Basically, in this function, some offset and the lengths are extracted from the message. Then you have this for loop, which is incrementing a variable called the byte position. And it keeps adding some length that we control to the offset. And this offset is used as an offset into the destination buffer. So at the end, we can out of bound write. And this leads to an exploitable stack overflow on the base. So now I will leave the stage, and they will explain to you how to trigger the bug.
Okay, I will talk about how we trigger and deliver our exploit to the baseband. So probably you will know that traditional to talk with the baseband, we need rely some open source project which based on the soft-defined radio tags. There are many open source projects that can help us to set up cellular networks, such as BTS, OpenBTS, which help us to build a GSM network, or OpenLTE or OpenL interface, which can help us to set up a LTE network. But you know that our case we find a bug in the CDMA, but since none of those open source projects do not support the CDMA protocol. So that means that we have to build a new project to support it, to write 1,000 or much more code to make a new project to support it. You know, we are hackers too, so we came up with different solutions. Actually, we built multi-protocol testers made by Rhodes Schwartz. This machine is used to design to test the signal and signal functionality of mobile stations. It supports different networks, including our targets, which is CDMA. So you will see that how we reverse this machine and patch it to make it satisfy our requirement to deliver and to trigger our bug. So we use this machine together with a Faraday cage, a shielding box, in order to gain better stability. And as well, we also use this cage to avoid any interferences. You know that you cannot disturb any common communications in the air, otherwise you may break the law in many countries. So we have to do that. And using this machine from the user interface, we can adjust the network parameters such as the country code, the network code, and even the channel numbers and so on. So after connecting a mobile phone to this machine, we can to this network which this machine make it. We can make phone calls and even send text messages from the interface. But it's a common tester, so we cannot use it to deliver our malicious payload. So we have to hack into this machine to make it satisfy our requirement. This machine contains different parts. The major part is so-called base unit, which including a main board and memories and hard drive. The base unit runs a Windows operating system, which is a quite old version of Windows. And to support different protocol stacks, different so-called optional link handle boards are needed. For example, if you want this machine to support the GSM, you need to plug a so-called B21 single unit on the main board. And to support CDMA, we need the B83 single unit. So take the short message as example. When the users try to send a message to the mobile station, to the baseband, he input the plain text on the interface, and the base unit will try to encode the message and send it as a so-called link handler message to the single unit. And then the single unit will add the headers and calculate the checksum to generate assemble the protocol-defined unit. And finally, this protocol-defined unit will send to the baseband via some channels. So our target is try to patch this machine to make it deliver our malicious payload. So we have to do some work on the base unit as well as in the single unit, so it can just make the payload just pass through the two units and directly send into the base station, a mobile station. So let me talk about the base unit. We reverse the base unit. The base unit is built on top of the Microsoft DOS and Windows. You can see the files listed in the right of the slide. And users can send a short message from the user interface or choose a predefined one to send. So it's all about the p-reversing work. So we are easily to locate the procedures that sending the message to single unit. Actually, we find a dynamic library in this file system, which probably means the CDMA 2000 mobile station. This dynamic library reads content from internal files and encode it and then send it to the singular unit as a so-called link handler message. The file is shown in the blue box in the slide. So you can see that we can specify the teleserver's ID, which is quite low-level parameters in the short message, P2P message. In our investigation, that we find that we cannot control the full barrier data, which is needed in our exploit. So we have to go further. In this stage, we patch the base unit to skip the payload length check and force it to upgrade the singular unit. You will see what is that in the next page. So another work is we have to make the singular unit works. So we find the upgrade functionality of this singular unit. The upgrading occurs when the self-check fails, which means the base unit, when the base unit boots, it will check if the singular unit works well. So if it's not, it will trigger the singular unit to upgrade itself to try to fix it. We find the firmware package in the file system and we recover the format by some reverse and some guess. So it's actually it's based on VxWorks RTOS and it's on a PowerPC architecture. So actually we are quite lucky this time. Hack3 has a PowerPC decompiler, so we can get the decompiled code, and we find the symbol and the name tables at the end of the file. And it's a very old machine, so there's no signature check, and it's only validating the checksum, so it can be easily bypassed. So finally, we locate some functions named the build short message in the firmware, and we patch it, try to patch it to carry arbitrary barrier data. And then we pack firmware and trigger the self-test to upgrade the singular unit. And then finally, we get our own gun to shoot our bullet to crash the baseband. So next, can you talk about the detail of how our payload looks like?
Okay, thanks, Mujing. And next, I will briefly talk about the exploitation part. And as you can hear, I got code recently, so pardon me if I don't sound clearly. Okay. So first, we need to do in the exploitation, we need to find a path to reach the vulnerable function. So the payload we should construct is basically a malformed CDMA 1x SMS transport layer message. So there are many fields and many structures inside this message, and we have to set them all correctly to reach that vulnerable function. So the first field we need to set is this message type message. We have to set it to 000 and to indicating itself an SMS P2P message. And next, the message actually consists of several TLV formats. They call it parameters in the specification. So this is a list of the parameters. Hope you can see it clearly. And the two one, as I said, red marked, and this is a two mandatory field. We have to set this teleservice identifier and the originating address. And next one, you can see here, this is a bearer data field. So although this field is optional, but since this field is critical to our exploit, and this field actually means the upper layer payload of this message. So actually it contains the data of the upper layer protocol. And this is where the vulnerable memory copy happens. So yeah, we have to, again, set correctly the data inside this bearer data. And similarly, the bearer data also contains TLV format structures. We call it subparameters. So the first subparameters inside bearer data should indicate itself a PIL message. So the structure of a subparameter is basically like this. Starts with ID. The 8 here means 8 bits, so it is 1 byte. And it has a 1 byte length and following with the length of the content. So as to reach that vulnerable memory copy mentioned, so we have to set the subparameters correctly inside the bearer data. So the first one is we have to set this message display mode subparameter. So the structure of the message display mode looks like this. It has many fields itself. And we have to set the message display mode to 0x03, which is 2 1 bits. And then we have to set the reserved field to 0x10. So as you can see, the PIL message is actually a vendor-specific feature. So it is not in the specification. So after we set all the fields correct, and it looks like we can reach that final vulnerable memory copy. So the basic function of that vulnerable code is actually sort the subparameters inside the bearer data. It sorts the subparameters by their subparameter ID from small to big, and that is where the buffer overflow happens. So it looks like trivial to exploit since there are no NX, no ASLR in the baseband, and no stack canary. Looks like a very classical stack overflow exploit, like in the 90s, smashing a stack for fun and profit. Looks a very easy task. So is it true? And next, so we are trying to do this, but we found there are many troubles we encountered here. So first of all, there are multiple code passes to reach that vulnerable function. And 2 of them are actually not very useful since they are only reachable. They are only used in an MO message situation. MO message stands for mobile originating message. That kind of message actually sends from your mobile phone. So you cannot reach this code path over the air. And actually, we found one code path that are reachable through an empty message, a mobile terminating message. But but we found that the buffer you can overflow is not on the stack. It is actually inside the global variable section. And yeah, we try to see what we can overflow, what we can overwrite, see if we can exploit. But sadly, we failed and we cannot exploit this situation. And at this moment, I just got confused who said it is a stack overflow. And yes, indeed, we do find a code path that, they test the buffer you can overflow did on the stack. But that code path is only used when the mobile station reads out an SMS from a USIM card. Seems not very useful since an attacker attacks over the air. So you cannot insert some malicious USIM card and trigger it to read your malicious SMS. So it looks like we are out of options, and since this way is a dead end. But since we are a determined hacker, we are a determined attacker, so there's old one saying, where there is a will, there is a way. So we again read all the source code, and we try to understand the whole process when your mobile phone receiving an SMS. And finally, we did discover a deep but very stable path to trigger that Stack Overflow. It is following this specific path. This specific useless path looks seemingly useless path. So what does the whole process of mobile phone handling a PIR message looks like? So first of all, it has to receive the message over the air, right? And then it will try to decode your message. And this is where your overflow could happen. But since, as I mentioned, the first overflow you can trigger this with a buffer not on the stack. It's not very useful. And then it will try to encode your message and write it into your SIM card. And just immediately after it writing into the SIM card, it reads the message back out and decode it again. And the second time decoding is where the stack buffer overflow happens, and this is where we try to exploit it. And so it's not a very trivial task. So our payload actually must survive the first encoding and decoding cycle. So you are not going to overflow the stack for the first time, you are going to overflow the stack on the second time. And your payload must survive this cycle. So this is not a very trivial task. So every time when you want to solve a problem, you will want to make it abstraction and make it a math problem. So we will do some simple abstraction, a simple math here. So first I will make the payload as x, and the decoding function as decode x, and the encoding function as encode x. So our final stack overflow option should be p. So our goal is actually to find an x for a given p, such that p equals decoding, encoding, decoding x. Right, this is right what we want. The first x goes through the decoding and encoding and decode again, and it becomes our stack overflow option. So as we are a hacker and we are trying to solve a mathematical problem, so we will always want to solve it in a more mathematical way, in a more elegant way. So we adjust our goal to another goal like this. So we are trying to find an x for a given p such that p equals decoding x and x equals encoding decoding x. So we can find here the x is actually the fixed point of the combination function, encoding decoding x. So with this condition, actually the p, you can see the p, you can derive it p from to the end, p equals decoding, encoding, decoding x. That's exactly what we want. And furthermore, actually, this kind of payload can go through not only one or two cycles of this encoding and decoding, it can go through arbitrary levels of encoding and decoding and survive all the time. So this is actually a very elegant solve, and this is what we want. And what's more, the CMU200 machine actually, we don't know how to bypass that restrict. It actually restricts your length of the TP layer message to be less than 130 bytes. And the buffer you want to overflow is 256 bytes long. So you have to make a 130 byte payload to overflow a 256 byte buffer. So this is not a very trivial task, but it indeed is possible. And yes, we successfully made it. And since the details is very complicated, so I will not talk it here, but you can find all the details in our white paper, and I give an example payload and all the process when the decoding and encoding happens, and you can see the payload stays the same when going through the encoding and decoding cycle. And furthermore, as I am a CTF player, so I adapted to a CTF challenge of this year's Zero CTF TCTF course, and name it Mighty Dragon. And this name actually comes from the code name of the modem we exploited. So if you are interested, you can try to see if you can solve this challenge. And during the game, only one team successfully solved it. So it is a very challenging task. So that's all for my part. Okay, Marco.
So at this point, we gain remote code execution on the baseband, but we are at the competition. We need to provide visual confirmation to the judges. But the problem is there is no display on the baseband. There is nothing, and we cannot just pop calculator like on Windows because there is no UI. So we decided from the baseband to change the phone IMEI, which is like a phone identifier. And this identifier can be checked from the settings of the phone. So after our exploitation attempt, the judge can just go to settings and see if we successfully changed the IMEI to 1337, 1337. So with RC, it's already quite a good capability for an attacker. Because it's running code inside the baseband, and from the baseband you can gain control. You can intercept and modify SMS calls and mobile internet traffic. So we will do a demo now. One moment. Oops. So here you can see the machine that we described to you and the Faraday cage. Here we show you the original IMEI, which is 8619. Now we will use the machine to trigger the exploit. And then now we will check if the IMEI is 1337, 1337. You can see the IMEI is 1337. So we point at the baseband. Okay, so the vendor response was very quick, and Huawei quickly patched the issue, releasing updates. And we had a good communication with their security response team, and we even follow up after Pwn2Own. And we had a very responsive feedback, and they seems to care a lot about the security of their baseband. So we talked about remote code execution on the baseband, but what can you do after this to get more capabilities? Well, I like to think it's similar to browser exploitation. In the browser context, you get first a browser bug and you get remote code execution. Then you chain a sandbox escape and you get like machine compromission. Here it's the same. The first bug might be a baseband remote code execution, and then you can launch another bug to escape the baseband. It's not a very well-studied topic, but there are some material on similar scenarios. We didn't have to provide this kind of proof to the competition because it was not required by the rule. But I recommend you to check out the Gal Beniamini of Project Zero research, where from the Wi-Fi chip, you use DMA to overwrite memory on the application processor, and the ComSecurity's blog post, where they use a path traversal in the MTK, reachable from the MTK baseband, in order to modify files on the application processor and escape the baseband. And after this, you can potentially get complete control of the target device. And the attack surface in this area is significant, and there is no public research. So now we will conclude the talk. Just to summarize, we show to you that baseband remote code execution not only is possible, but also practical if you are a determined attacker. Second point, baseband are very complex and they have a huge remote attack surface. Third point, they are written in a memory unsafe language, C and C++, and they lack of even basic mitigations. So it should not surprise you if someone can get a remote code execution on baseband, given those two facts. And we hope in the future to see more mitigation on the baseband, and maybe in the long term to see that the baseband are written in some memory safe language. And but this cannot happen in a short time frame, so maybe in the meanwhile more people should audit baseband. And we would like to acknowledge the following of our colleagues. And thank you everyone for attending our talk.